Hello everyone, April 11th. All right, I think I will get the tablet, drawing tablet. I think earliest it will arrive maybe next week. Well, anyway, so today's goal. All right, we'll get this one done, right? And we'll go back here, which means we have to go back and learning this thing. And in fact, what I'm gonna do is, because I have something called useful snippet, right? If you see, we have a useful snippet. So right now in the useful snippet, I have binary index tree and union find. I think I need to put this thing in, this lazy segment tree in it. It's definitely necessary to put it in it. So we'll deal with this later. And once we can deal with this, we know how to solve this already. So that's not a big issue. Okay, so here, simplify path. I see. It's a stack again, all right? Okay, absolute path. A dot, the current path. Double dot is previous, yeah. I'll treat it as a single slash. Okay. Any two directories are separated by a single slash. What about double slash? Oh, double slash is treated as a single slash. Contains the directories in the path from the root to the target. The path only contains the directories on the path from the root to the target, no period or double period. What does it mean? Not double period at the end, right? So for example, this, well, there's no trailing slash after the last. The canonical path is, we don't have an ending, okay? And this will be this, yes. This, multiple consecutive slashes replaced by a single one. Multiple consecutive. I mean, we can just split on this, right? Actually, I'm not sure. I forgot. Split on this. What we're gonna get? Home. Foo. Let's do bar like this. A dot split. And split this. What do we have? Perfect. We just skip. All right, we'll skip. And then we'll push into the stack. Right, we'll push into the stack anytime it's well, what if we have multiple dots? Or if it's a multiple dot, it's treated as a directory name. So it doesn't matter what's the start. We don't push it in. So at first we'll push home, and we skip, we push full, skip, push bar, and skip, done. And then at the end, we just add a front slash. Yep, that shall be it. And then if we have a dot, we don't make any change. If we have two dots, we pop. I think that shall be it. No, I don't want TypeScript. Okay, so we need a stack, right? And then we say for element in path dot split this if element, and oh, actually we should do this. If element is equal to a double, right? Let me say if stack dot pop. Okay. If element is equal to a dot, then we'll continue. And if it's not equal to a dot, okay, if it's equal to a dot, then we continue. If element is not equal to a empty string, right? That should be the actual thing. Then stack.append element. Can we simplify this? Basically just mean the single dot and empty is the same thing. So maybe we can do this. If this and this, then stack.pop, right? If this is not equal to and element, then we will append. And our return, we have to add this plus join. Ooh, this stack. Okay, I'll give this a shot. Oh, you better be good. You better be good. Oh my god. Wait. Oh. That's... Okay. It's fine. We can put this one at the front. All right? We'll put this at the front. Then it will never be empty. Yeah, then we will have to check this. Ugh. What should I put at the front? An empty string? I don't know. Empty string? Try it. This is not right. Because in the second one, if I put empty string, it will pop. It popped the empty string. Okay, now we just do this then. If stack, else, we return this. I mean, might as well just do this. All right, and stack. It's fine. It's fine. And this one will be fine. Oh, then this one will not pop. Oh, screw me. Screw me. I'm gonna try? Yeah, let's just try. Hey, I got it right last time. Come on, man. Alright. I don't know, maybe I took a few more try last time. That's okay. That's okay. I thought we can just, you know, do it without too much trouble. That's okay. That's okay. This shall return this, right? And then home foo shall return home foo. So which one we got wrong? Huh. So basically it's at the end because you do this join. Oh. Okay, so I think we just need to put this at the front. Then we have double. Why do we have double on this? Interesting. Well, that's because we have this at the front, right? I see. What about this? If this, and we should say if stack, then we pop. If no stack, then we don't do anything. Right? Like that. Hopefully this one it works. Come on. Yep. Took one try. Yeah. Not ideal. Not ideal. But anyway, it's still stuck. Still stuck today. 71. Still stuck today. Alright, nothing more to see this one. I don't think we have any interesting solution before. I think it's about the same. Stack. Yep. How about this one? Ew, this one is ugly. Okay, done. Alright, let's do this again. Segment tree with lazy. Okay, so we have the general idea how segment tree work yet today, which is good. It's fine. All right, lazy. So what we want is given a range, right? You want to modify values in a range instead of just a single. So you need to use lazy propagation. When there are many updates and updates are done on a range, we can postpone some updates and do those updates only when required. Remember that a node in segment tree stores and represents the results of a query for a range of indices. And if this node's range lies within the update operation range, then all descendants of the node must also be updated. That is correct. For example, consider the node with value 27. 27, okay, 3 to 5. This node stores the value 3 to 5. If our update query is in range 2 to 5, then we need to update this node. That is correct. And all descendants of this node. Oh, are we saying that we stop at 3 to 5? We stop at 3 to 5. Don't keep going, but just stop there. That's interesting. This stores the sum of indices. With lazy propagation, we update only the node with value 27 and postpone updates to its children. By storing this update information in separate nodes called lazy nodes, we create an array which represents a lazy node. Size is the same, which is 3. The idea is to initialize all elements of the lazy node as 0. A value of 0 indicates that there are no pending updates. A non-zero means that this amount needs to be added to node I in segment tree before making any query to the node. But it still requires that everything inside this range to be the same, right? So everyone inside this range need to be increased by the same amount. Hold on, let's see again. Update range. If current segment tree node has any pending update, then first add that pending updates, okay? If current node's range lies completely in the update range, update current node, postpone updates by setting lazy value, okay? If current node's range overlaps with the update range follow the same approach as simple update recursion for left and right children. Update current node using result of left and right calls. Okay. There may be problems if a query is made to a node that is yet to be updated, so we need to update our query method also with the getSum. Now first checks if there is a pending update, and if there is, then updates the node. Once it makes sure the pending update is done, it works the same as the previous. All right, let's take a look. Tree update range utility. Okay, so if lazy value is non-zero for current node of segment tree, then there are some pending values. So we need to make sure that the pending values are done before making updates, because this value may be used by parent after recursive calls. See last line of, wait, what does that mean? But anyway, so if it's not equal to 0, that means we have a pending. So if we have a pending, we make pending updates using value store. So this is yeah, that is just telling you in this range is exactly the same. In this range we have exactly the same value. That's segment end minus segment start. That's how many in there, right? And it is a current segment, and every segment needs to be added to the same value. But what if it's not the same value? Like in this range, because we're doing exclusive OR. We're not exclusive OR. We're doing toggling, right? So if you say you want to find the number of ones in this range, we update the number of ones in this range, and in this range we can issue multiple, like all the consecutives we can do, right? Just one, right? Consecutive is just one. So like from this range, from this put to the next, they all add 1. Right? That makes sense. So the lazy, this is delta. This is the delta. But then you still have to go through the whole thing. I wonder. You still have to go through the whole thing. What I'm saying is you have nums1, right? First query. And you have your, now queries here. You have your range. If this range is huge, all right? Because this range can be what? Around R. nums1 dot length, nums1 length is this, right? So this can be a giant range. If you want a giant range, everybody to toggle, right? I want a whole thing, everyone to toggle. Then you need to find out where the one's gonna be. So the places that are ones, the delta will be 1. The place of zeros, the delta will be 1. The places ones, the delta will be -1. And I don't know, man. This still seems, I mean, if you have a large range, that would be fine. But what if it's just like 0, 1, 0, 1, 0, 1, 0, 1, things like that? You have to issue query every single time. Now you issue the segment tree every single time. How is this faster? You have to do it n times. I feel like this is another level in this. There's another level in this. Because the range are not the same value. Yeah, that's my issue. But anyway, we need to finish this one first. So we update this, right? And then we check if it is not leaf node. Because if it is leaf node, then we can now go further. But if it's not leaf node, yes, we need to propagate into the next level. Okay. And set the lazy value, yes, because we have done it already, so this lazy value is set as 0. This is out of range. If current segment is fully in range, which means the segment start is larger than update, segment end is smaller than update, then with the segment do this completely, the diff, and then the same. Oh, the diff. But no, that's not the same. It's not like saying everybody in this range is going to add the same value. That's not true. Let me think again. If we have, let's say, 0011, right? And I change the middle to, all I need to know is the total number of ones, right? That's what we need, the total number of ones. The total number of ones. Yeah, that's what we need, the total number of ones. And we'll make the toggle, right? If we make the toggle, are we saying that if we make the toggle, then if I have 3 ones and 2 zeros original, right? Then we make the toggle, then we have 2 ones and 3 zeros. You can say that the total number of ones decreased by 1. And are we saying that in this range, the delta become -1? I mean, we can do that, right? In this range, we can do that, but it's not going to be right, because if you do, it's not like everybody in this range gets delta, change the delta. It's not like that. Because you could have some points which originally is 0, we have no ones, right? Now we say we're going to decrease 1, and those places will become -1. That doesn't make any sense. No, that does not make any sense. Let me think again. What if we have the ranges of all ones initially? Okay, so we have all the ranges that were 1. And then when we have a new range coming in, let's say we're gonna do whatever we need to do, and we'll toggle, and that will change. Ooh, and then we have, man, I don't know. I don't know how you can make this easier. Yeah, my problem is the segment tree. In my mind, the segment tree with lazy evaluation requires you to have the update of a segment to be the same value. Okay, which means if we use it to on the first query, we need to find the range of all ones after the first query. That's what we need to do. And the first query, the range is huge, right? Then how are we supposed to find all the range that is 1? We have to go through them one by one, which is, ridiculous. And not only that, we have to keep the values, right? We have to keep the values because the next time we do it again, it will change. And, it's 10 to the 5th. Right? It could be 10 to the 5th, and then the query length is 10 to the 5th. I mean, it will not all be the first query, that's for sure. But if we have a lot of first queries, all right, I'm gonna finish this. I'm gonna check the solution. I don't know. I think I'm in the wrong path. All right. Anyway, so where is the? No, not this one. This one. Yep. If it's within, we do this. If it's not, we do this. That's perfect. If not, then we split in half and do this and do this. Ooh, we have one more. What's this one? And use a result. Oh, well, this is just use a result. Okay, update range. Okay, this is a get some utility. If it's not equal to 0, we have to update it and lazy it. If start is larger than segment start is larger than segment end, segment start larger than query end, segment end that's 0. Pending lazy updates are done for current node, so we can return value. That's true. Otherwise we do this. Okay, but I don't see how this one can be used. All right, let's take a look. Segment tree. Convert to binary and use exclusive OR. Dude, how are you gonna convert to binary? There's 10 to the 5th. Yeah. Yeah. It does not TL. It does not TLE. Yeah, this should TLE, right? Oh my god. It did not TLE this thing. Okay, that's this is okay. That's not the purpose of us doing this problem. This is the one. All right, let's see. How do you? I mean, we don't. I don't need to see the tree itself. I want to know the idea. To update and create the first. Yes, that's the thing. Wait, how do you? I still don't understand. How do you? Anyway, this is update, right? Doesn't matter how this one is implemented. It's just a lazy. And how do you do build a segment tree? I think this is to build a segment tree, right? And if update, huh? Update tree, what's n? I think that's the diff. This is the range. No. It's from 0 to 1 or from 1 to 0. How does this make sense? It will flip from 1 to 0. This just says we'll update everything to 1. I don't understand. This just tell me to go from this and everybody to update him to 1. How is this accurate? Exactly. How is this accurate? Maybe there's some further tricks inside. I didn't know. Because you cannot just update everybody to 1. Because there could be some 1 in here. Do we have another segment tree? Okay. That doesn't matter. Sum of interval will be len interval minus sum interval. Oh, that's slightly different than what I had expected. Huh. It is update. I think this is to use to flip. Oh, I think I know. So the operation is not addition. The operation is Lordy. The operation is exclusive or. That is for exclusive or. And then you just add them up. Yeah, you look at this. Segment tree 1 times j. Right? You just add them up. Oh. Okay, so this segment tree implementation, right? What we're doing is you will add this value to every single one. But what we are handling right now is you will not add, but this is the exclusive or. All right, so you're saying, given this range, every single one will exclusive or this thing, right? Will exclusive or this thing. So when you build, oh my god. So we need to build this tree. How do we even build this tree? So each node is still the sum of all the ones in this range, right? We can still build it the same way. Which is an update. But what do you update? You update with... You cannot update with anything. The update has to be different when you build a tree. Anyway, if you can build a tree, right? If you build a tree, then each node will record the sum of the total number of ones in the range. Okay, so that's just a regular segment tree. And then when you update, you say, I'll update the certain range, and everybody in this range will exclusive for with 1. And then you say, okay, I will do this range, exclusive for 1. Then what? Then, yeah, I still have the same issue. Hold on, let's see. Okay, lazy. Oh, what the hell is len? This is a tree. Initial length and summation. Initiate length, initiate summation. What's the length and if we're going to flip all the values in the interval, the sum of the interval will be the sum of the interval. It will be the length of the interval minus the sum of the previous interval. Yes, true. So we need to record the length. The length. What are you talking about? The length? Huh? The length of each interval. and the initial summation of each node. Wait, so this is the length. What's this? This is the index. What's this? ULUR. Current. I think this is the segment, right? I don't think he even uses ULUR here. Self.len, and this equal to 1. I'll return 1, and then we do this if they're not the same. Oh, you don't have to do this because you already checked. Anyway, you initiate this. Yeah, you didn't even do UL and UR because initiation, you just have the range, right? If the range is outside the range, return 0, the length is 0. If it's 1, it'll become 1. Otherwise, you'll get because this is the query, this is the segment. So query will getting half. Wait, is a segment getting half? No, segment will getting half. CLC, that's the segment, right? That's the segment. So segment will getting half. And segment getting half. Oh my god. Segment getting half. And update range, those never change. You see that? Those never change. The segment getting half. Okay, segment update range. And a segment getting half, right? So segment start to mid, update start, update end. Now I only do this part, right? Whenever it gets outside, then that's it. So the update range never changes. It's a segment. Okay, segment getting half. And we have a segment start, segment end. And it will be a certain time, it will be out of range. Okay, that makes sense. But anyway, this one just get the length, right? This one get the length. This one get the sum. What's this num? Nums. What's it initiate? Nums 1. This is the count. No, not count. This is the, right, this is the count, right? This is the count. This is the total count. Okay, I can get behind these two, which is fine. This is update. Okay, so as update left, update right. I think this is a segment, right? So if Update left is larger than, the second behind. Update left is smaller or equal to, and so everybody is here. And we'll update this individual specifically. So that's update only one of them. Self.lazy will update. And self.tree land individual. What's this lazy? Minus self.tree. This is the total length minus the previous. Okay, I can get behind that. That's update. Right, this is the update is covering the entire, so we have the range. This range completely have to update. Otherwise, then cutting half, then we will propagate and update left, update right, self.tree. If the parent node has the notation to flip, then we update all summation of children nodes. Self.lazy. Oh, what is this? Wait, what is lazy? What does lazy store? Oh, this is actually a smart way to do. Actually, I want to. I'll take this. Wait, what does lazy do? What's lazy? And we query. Populate lazy. Propagate lazy. I don't know. I have no clue. I have no clue. What does this lazy do? Where does lazy first show up? Lazy is 0, right? And then when we do the length and the num, lazy never shows up. And when we do this, lazy starts to show up. And if we do J and K, right? That's the range. When we update this range, given a current segment, and at the beginning it has to be this, right? And then we will and if it's initial 0, so we don't do anything, right? And then we just update. So we keep updating. And when we first start updating, this is all going to be 0, the first round. So eventually we'll hit the end, okay? We'll hit the end. And something gets turned into 1. And the tree gets the length minus the original. Okay, that makes sense. And then as we go back up, So the first flip, right? The first flip, what I have is at those positions. So these are the final positions, So they indicate the actual positions of the single node. They are these things. Individual nodes, okay? They are individual nodes. I will mark a flip. Basically, we'll just say, at this point, what it is, right? If it's a 1, then they will become a 0. And if it's a 0, they become a 1. But hold a second. Initially, everybody is 0, right? So this just means if I have flipped or not, right? It has nothing to do with the actual count. The actual count is handled by this operation. Okay, so we're just saying at this position, everybody in the range represented by this individual, this node, has a flip. Everyone has a flip. And when we do it again, so every time when we do, if at a certain point we have a full range. Yeah, because we have this will be 1. And the next time, if it comes again, and we need to check, right? We need to check if this node has any, is this node flipped? Has this node flipped, right? If this node has been flipped before, then its children needs to flip. We need to flip the children. Oh, this is an important concept. If I have flipped this node, but it's lazy, so I haven't flipped its children. So I flip its children. I would say the child needs to be flipped, and its count needs to be updated. When you flip a child, you do this. And you flip the other child, you do this. And then you update this. That is correct. And you reset to 0, which means you've finished the flip. There's no more flip in this. Holy guacamole. Oh, this is hard. So I think the reason I couldn't figure it out earlier was I'm always thinking when you update, right? Because we want to find the total number of ones given a range, and I will update and then find the total number of ones. But that you just cannot do, right? Because you don't know where the ones are. Now this solution points out that you do not need to know where the ones are to find the total number of ones. All you need to do is know the length of a segment, which honestly I don't really think you need to use a tree to do that. You just want a segment, right? You just want a segment indicated by a node. Yeah, it might be easier if you do it that way. Because you've given a node, you actually don't know. Well, you actually do. Because this is your range. These are the ranges, right? These are the segment range. And you know the length at the current, like this is equal to CR minus CL plus 1. You know that. You know this value, right? And when we propagate, you can just put the current range in. But what about the next one? Then you don't take it out. But you have to propagate in both places. Oh, what? I'll just rewrite the whole thing. It's fine. Since if I do that, I can avoid using this thing. Yeah, this thing is just not necessary because I know this, right? I know this is just mid, right? Mid minus CL plus 1. So yeah, so the point is for each range, right? If you have its original number of ones, and if this range has flipped, then the number of ones is the length of the range minus the total count of ones previously. That will be the new count. And if you flip again, it will change again. So that is how you get the total number of ones in any range. What we need to reduce is the number of propagation we need to do for the flip, right? Because if you say you're giving me a range, I'll flip everything in this range, which is exactly what the problem is. You have from L to R, and you say want to flip everything in this range. And if this range happens to cover an entire segment, then this entire segment will need to flip. Then all you need to do is to record that this segment will flip, right? You record that, and we're good. And then you just lazy propagate that. Yeah. And then we go back here. Let's take a look here one more time on this thing. Right? So for this to lazy propagate, you just need to plus equal to, right? Which is, fine. It's fine. If you take a look at this, when you update, right, we'll check, and then we'll update. Which actually can be the same here, right? You check and you update. Do we even need to update these here? I don't think so. I do not think so. I think we can follow this template, right? When you update, you say if this is not equal to 0, which means it has been flipped. Think about the flip. It has been flipped. And once flipped, your tree needs to update. Now we have our own way of updating it, right? And our own way of updating is not this. It's not this, but our way. And when we update it, then we'll see if the current is not the end, then we need to propagate. Then we will propagate. Basically just exclusive OR with 1. We flip and flip. And then we do this, and then we do this. And it's full in range. If it's full in range, we don't do this, right? Oh, we do this. Oh, it's slightly different. Okay, hold on. This is say when we update this range, we check if it has been flipped. If it has been flipped, then we do it. And then we propagate the flip to the next level. And then there's no diff. There's no diff. We just do this. We don't even have to do this. All right, we already propagate the diff. We already propagated, so we don't even have to do the remaining. Right? Is that right? Because there's no diff. There's no diff. Overlaps, we just update this and this. And we'll add yes. So what you're saying is we have to first compute we have to first build a tree by count, which is okay. We can do that. So we'll build a tree. And after build a tree, we need an update, right? And we need an update, and we need a query. And a query is the same thing. We'll query. Same thing, like if it has been, like my current node indicator has been flipped, then I'll flip it. Right, I'll flip it. Then that's it, right? If I flip it. I flip my range, like everything in this range. I'll flip it. I get a new count and then propagate it down. Right? And if it's within range, but do we even do this again? The total number on I have this range, right? And I need to flip it. That's all. We just need to flip it and then we're done. We get we say this one needs to be flipped. I say it's not, it does not need to be flipped, and then we go down. And if it needs to be flipped, then we flip it, and then we go down. And the count of this range, that should be the same. I think I'll stop right here. Yeah, this definitely needs one more day, and I want to do something different from this. I think we can do something different. Right? I think we can do something different. Because there are a lot of things. I feel like it's like this, I call it here. And this, I call it again. I think it's redundant. Right? I feel like it's redundant. All right, we'll try this again tomorrow. This is tough. This is tough. All right, I will try this tomorrow. See you guys tomorrow. Adios.